Hello, everybody. Welcome at this session where we are going to talk about ships. Um, People working in machining applications are well aware of ships. It's one of the things which are created during a machining process. And most of the time, when you use the word ships, everybody starts thinking on a situation like the one you see here on the video. With other words, ships equals problems. That's in general how people see the aspect of ships in machining. In this presentation, I'm going to try to let you understand the other side of a ship, because ships mean trouble. But sometimes I say ships mean trouble for the careless, those who do not know. But for those who know what a ship is fully, a ship is a treasure. A treasure with what you can do a lot. My name is Patrick de Vos. I'm your host today. I'm more than 40 years in machining, so I collected quite a big amount of insights. And over the years, I kind of created my own model or concept, one could say, about the machining process. And one part of that concept is that understanding a machining process for me means that you need a collection of knowledge inside the physics side of machining. What's going on there? Cutting forces, heat, temperature, all of that. You also have to have insight in the practical side, kind of what we call expertise. Expertise, as I see it, is okay, I understand now what's going on, and that knowledge I use to influence the process. That for me is expertise. You need skills also, and skills is about making it happen. You have the knowledge, you have the insight, you know what to do, and then being capable of doing it. How do I manipulate all the elements in a machining process, and experience in production, because machining in the industry is more than a technique, it's more than a process. Machining is something people in the industry use to create workpieces that they create with an economical purpose, to sell them, to make profit out of them. So that is also a part of machining in my eyes. But even if you possess all of these knowledge and skill and insights, what we notice also is that machining means that ships are generated, that used tools are generated, and every single ship which is formed is different. And every used cutting edge looks different. And if you think about it, if you have a process and everything is fixed, why is not every ship the same then? Why is not every used cutting edge the same? And the third part, which is a reality, is that some of the parts we produce are no good. So you have a process, you established all process parameters, you make a workpiece, one is good, the next one is not good. And that leads me to kind of a conclusion that in machining today, there's quite a lot of chaos. Chaos, I defined it as I have a number of parameters which I do not change. I make them work together. I look to the outcome, the output, and the output is not constant, is modified. So it means that there are things which we forget, we overlook, we wrongly estimate. And the one we are going to talk about today is the ships. And some of you perhaps have heard me talking also about something which I call GTDA, which is a methodology, which is a concept to analyze used tools. GTDA stands for Global Tool Deterioration Analysis, which is a method that gives insight in the practical machining process, not part by part, but the total picture, in the total workshop, one kind of could say. And based on that insight, I can appreciate the actual machining process, to which level I have it under control and where I need to optimize or to improve or to correct. But GTDA has a disadvantage, and that is that it's measuring offline. It's measuring how a tool looks after the process, meaning that whatever we see, whatever we learn from it, kind of is late for the process which is just finished. And that is not a big problem if you talk about big batches, where you have to produce thousands, tens of thousands, perhaps even hundreds of thousands of workpieces. And what you learn from the first one, you can apply in all the other one. But if you talk about small batch production, where perhaps you have to produce only one workpiece, yeah, you learn after that one workpiece that the reason why it was not good is this or this, yeah, but it's kind of too late. The other thing, and that is what we are going to talk about today, is that you can analyze the ships. And also there is a methodology, a concept, a model, whatever you want to call it, which I refer to as GCFA, Global Ship Formation Analysis, where we look at the ships, the shape, the size, the color, the whatever, every aspect of a ship. We do it in process while the ship is being formed, and if we know what to look for, the ship as it is being formed tells us how the process is going. And that is something I would like to already point out here, that a ship next to problems, issues, is also kind of a signal to us, if you know how to pick it up, a signal online in process that tells you how the process is going. So in process, you can correct if needed, depending on what the ship is telling you. All of these aspects on ship formation, I would like to refer, because we have only 1 hour today. We can't do everything, or we can't discuss everything today. Although I would say, if you have questions, please put them in the comment. At the end here, we have a question and answer session. But I would like to point out also that there are pocket guides available, and one of the pocket guides is noticeable, discussing on ship formation. It's 80 pages, knowledge about ships, where you can find a lot more. I'm of course not alone. As always, I have 2 lovely ladies here who are taking care of the technology behind this broadcasting, because I have the easy job here. I stand and can talk to you, but these 2 ladies make sure that everything in the background is working well, and that all the promises I make are fulfilled afterwards. So thank you to those 2 also. And the agenda for today looks that I want to talk a little bit, the time is limited again, about ship formation. How is a ship formed, and what are the different types of ships? I also want to talk about ship evacuation, because it's not only enough to control how a ship is formed, we also have to be on top. We have to be in charge of how the ship evacuates away from the process, because also there a lot of issues can happen. We are going to discuss a couple of the elements influencing and ship formation and ship evacuation. And the last part I want to talk with you about, that GCFA system. How do I monitor ship formation in process, and how do I act, how do I react with all that? Now, ship formation, there are 2 types of ships basically, which gives us in reality very often issues. That is the long stringy ships that see the photo on top here, that turns around the workpiece, that is dangerous for the operator, that needs the operator to stop the machine, to remove the ships manually, and so forth. And then there are the very big ships, the heavy duty applications, where ships are very big and difficult to handle due to their size. If we talk about ships, what we need to talk about is the type of ship. Is it a long ship, a short ship, whatever? The size, as I already said, how big is it? The shape it has, and how is the behavior of the ship? Because these things are going to influence how tools wear out, the surface finish on a workpiece, dimensional accuracy of the process stability, and so on and so forth. And if we evaluate ships, instantly we talk about good and bad. What is a good ship? What is a bad ship? And defining that, normally people look to technological stuff. They talk about a good ship must make that the process is smooth and reliable, that there is a good heat balance, that tool life is well under control. And there are a number of technical things like that people use to look at the ship and say, okay, this is good, this is not so good. But next to that, because as I already said, machining is more than just a production process. In the industry, it's also a process we use to generate products. That means that there are economical and sustainability targets also. And if I take those two now and look at a ship, a good ship should also not create hidden costs. What do I call a hidden cost? If a ship is too long and it's around the workpiece and the operator has to stop the machine and remove the ship manually, that creates a hidden cost. Because everybody thought the machine was running, but actually the machine was not running because the operator had to remove the ship. Scrapped workpieces can have a hidden cost. And workpieces can be scrapped or at least need rework due to ship formation stuff. Ships that scratch the surface or something like that. And the sustainability part in it, there should be no minor machine stops due to ship formation, because that's going to endanger the flow of the process, safety of the operators, because ships have especially not the good ones, are not so nice for operators. But also from a recyclability perspective, ships should be easy to recycle, easy to be handled, and easy to be recycled. So the definition of a good ship goes beyond pure technical stuff. And if we look to ships in reality, in a workshop, normally we say the ships to the left, the spiral-shaped ships, that are the good ones. They combine quite a lot of advantages and have very little disadvantages. And compared to that, ships can be too short or ships can be too long. Too short ships are mostly dangerous for the process, because they one of the things you will have to suffer here is micro vibrations, which will lead to premature end of tool life and so, or could lead to premature end of tool life. So too short ships is more a process related thing. Too long ships is more a ship evacuation thing. The ships itself are nicely formed, but it's an issue taking them away from the process. Now, this is very nice in theory. In reality, that spirally shaped ships, it's very often a dream thing people are chasing, and it's not so easy to realize. That's why most of the time what we say is that if you have short, nicely formed ships, the one you see here in the middle, that is what we want. And compared to that, ships can be longer, too long, and then you have a ship evacuation issue, and you should take care of it. Or ships can be of the type, what I try to show here with the photo to the left, which we call overbroken ships. Ships which are not nicely formed, but kind of forced in a certain way. And those are also dangerous for the process then. Here you find, after a while, the cutting edges that will suffer from this. So short ships is what we chase, especially from a technical perspective then. Compared to that, ships can be too short, the so-called overbroken ships, which is dangerous for the process. Ships can be too long, the long ships, the whatever shape in long ships, and that is more a ship evacuation issue we have to handle them. Now, if you stand there looking at the process and you see the ships changing while you are machining, yeah, that's a signal. Remember my chaos thing. If a ship changes form during the process, it means that something is changed. And you should be observant then, because it could turn out that it's a good thing. It could also turn out that it creates an insecure thing, an unreliable thing. And then you have to stop, because otherwise you end up in problematic situations. Now, ships, there are basically four forms of ships. There are what we refer to the continuous ships, the long ships, which are very typical, formed in materials with a high ductility. You can deform easily without breaking the material. Materials like soft steel, non-ferrous materials. These are the materials where you find long ships. The advantages are they are nicely formed, lower cutting forces, less power. It's a smooth process. The disadvantages, however, are big, because these ships are quite difficult to evacuate in an efficient manner away from the workpiece, from the process. These ships will lead to extra standstills of the machines, minor stops. The operator needs manually to interfere here. If you are confronted with long ships that become problematic, think in terms of you can use ship breakers, different ship breakers. You should increase the feeds. You can work with cooling. High pressure cooling could add that little extra thing to make a ship shorter. Another type of ship, the opposite of a long ship, is a discontinuous ship. The very, very short ships, which you find in materials with low ductility, cast irons, for instance, bronze, the hard plastics. That's where you find this type of ships. Here you have a bit of the opposite situation as the long ships. The ships are easy to evacuate. Unless you end up in dust ships, then you have some other issues to take care of. But anyway, in general, easy to evacuate. But for the process itself, it creates a constant change in cutting forces, pressure, and that type of things. And it's a challenge for the process, this type of ships. On top of it, mostly this low ductility is very often combined in those materials with a high abrasiveness towards cutting edges. So there we have those things to take care of. If this is really on a problematic level, use tougher cutting materials. That's a kind of a diplomatic thing. You make the cutting edge more adapted to handle this situation. Also here, bigger feeds, or at least consistent feeds, is what you should chase for. And on a cutting edge, be careful with micro shipping from a wear perspective, because that will be an important phenomenon here. Then you have, I don't know, I call it the build-up edge ships. Some materials show a tendency to connect to the cutting edge, to the tool. And if that happens, the ship which is formed is influenced by that. It's a very irregular, randomly formed ship. Very typical, a ship that comes with kind of another issue you have during machining, namely that the build-up edge is formed. Advantages are hard to find. That in theory, one could say, yeah, but if such a build-up edge is formed, it kind of protects your cutting edge. It's a very nice statement, but in reality, it's not so easy. The disadvantages are more serious. If you have a build-up edge phenomenon during machining, the ships which are formed when you have that are totally randomly formed. It's impossible to control them because they change every second. And if you have this situation, increase the cutting speed, use sharper tools. Cooling system is the other thing to look into here. And finally, you have the serrated ships. Serrated ships are the ships you'll find very typical in the or materials that are harder steels, for instance, or materials that have a higher strength. I think here on titanium, superalloys, that type of materials, where ships are of the serrated type. The advantages are they are easily evacuated, let me put it like this. In general, they have lower cutting forces when they are formed, which is a good thing for the smoothness of the process. But the disadvantages is that these are rather aggressive ships for the cutting edge, and they will influence tool wear and tool life seriously, mostly in a negative way. If you have this type of ships, the serrated ships, and if you judge them being problematic, it's about feeds, higher feeds, lower engagement zones, try to reduce the interrupted load situation on a cutting edge, and so on. This is very short. Again, we have a time limitation here. Very short, but again, if you think on reference materials available, you find much more information about these 4 types of ships. But from an evaluation perspective, these 4 ships comes for typical workpiece materials. You have to accept that, and each of these 4 types of ships, they have advantages. Although for a build-up edge ship, it's doubtful to talk about advantages, I would say. And they have disadvantages. And it's a balancing exercise you have to do here. And that balancing exercise, you have a number of elements you can play with. Elements related to the cutting tool, elements related to the machining conditions, elements related to the workpiece materials, and elements related to the cooling system you use. Now, if we think on workpiece materials, I think most of you are familiar with that so-called ISO system to classify workpiece materials in 6 families, 6 different groups. And one could say for each of these groups, it's kind of possible to connect a very typical ship formation process to it. Steel, very typical, gives long, medium-sized ships. While cast iron gives us the short ships, the discontinuously formed ships. Workpiece materials is an important element in the process. Tool geometry, I let the video talk for itself. If you change the geometry of a cutting tool, the ship formation process itself is changed. And when the process that forms the ship is changed, the result of it, the ship, is also different. When we talk about tool geometries, it's the macro geometry, the cutting angles, the rake angles, and that type of stuff. But it's also the micro geometry, how a cutting edge looks. Is it sharp? Does it have a chamfer? All that type of stuff. Cutting conditions. I think this is one of the most known pictures or images in the machining world. It's an image that gives us the relation between the depth of cut and the feed and the type of ships which are formed. It's a so-called ship breaking diagram. And here you can see that how you combine cutting data, the depth of cut and the feed, the form of the ships you will observe during a process is going to be changed. And then we can say, okay, I accept the part here in the gray zone, these are acceptable ships. And if a ship falls out of the acceptable domain, this also learns us how to act on it. Should I increase or reduce cutting conditions, with cutting conditions? It means the material is the leader in this thing. Typical material, typical ship formation process. Influencing it is something you do by your geometry selection for the cutting tool, and how you connect or how you combine cutting conditions with the selected tool. There you make it all, or you bring it all together. I'm missing one here. A very important one which is always forgotten, but I'm going to take that in a few minutes from now. In the meantime, I would say what do you think? Which element here is missing if we talk about ship control? Put it in the comment. I'm very interested to hear, to see what you think that is missing here. Ship evacuation then, once the ship is formed, it needs to be evacuated. Because if a ship is not evacuated, perhaps it's less dangerous for the process, but for sure for the operator it's a dangerous thing, and it's going to lead to machine standstill because the operator manually needs to interfere to evacuate the ships out of the cutting zone. If you don't control ship evacuation really fully, it also will lead to potential damages on the workpiece and on the tool. Think on drilling operations where you don't manage to evacuate the ships out of the hole. Ship evacuation, the tool geometry plays a role, the cooling system you use plays a role, the machine setup you have plays a role, and the awareness of the operator that yes, he must do something, because having long ships which are not evacuated, very often an operator say, yeah, that's the game. It works like that. It's a kind of a cultural blind spot. It's not the game. Ships should be evacuated in an efficient way. Operators should not accept that. Tool design plays a major role here, and I would say the flute design, the helix angle, and the ship removal grooves on a cutting tool. And I'm talking here mainly on milling and drilling tools. That are the tool design elements we play with here to control how ships are evacuated. Because remember, if you don't evacuate ships in an efficient way, ships are going to hinder the process, are dangerous, lead to damaged workpieces, and so on. And a correct tool design should take care of those things. Make sure that the ship, whatever form it has, is evacuated in the most easy, smooth possible way away from cutting edges. Cooling plays a role here, because people use cooling to influence tool wear, tool life. People use cooling for lubrifications, to keep temperatures lower, and so on. But cooling also is something we use to flush the ships away. And here I think especially on high pressure cooling systems, high pressure direct controlled pressures, cooling systems, and so on, which are a very useful, helpful way to evacuate ships. Machine configuration, yeah, the vertical or horizontal machine, ships go away from the process and then fall down. So gravity makes sure the ships fall down, and depending on the design or the configuration of a machine tool, that falling down is off workpiece or in the workpiece. So it's a big difference. So that is that part, and the operator awareness, as I already said, it's the operator today that has clearest follow-up on what is happening with the ships. He sees them, he can feel them, careful with it. He hears them when they are formed, and he can act on it. So ship evacuation is a dynamic thing. It's not because it works 5 seconds good that you can rest assured that it will go on forever like that. You constantly have to keep your eyes on. And the result, or the negative result, if you fail to evacuate ships in the best possible way, is damaged workpieces, damaged operators, damaged machines, crashed tools, and so on, all leading to that the machine has to stop. Workpiece materials, every type of workpiece material, the ISO system leads to a certain type of ship. There's no use trying to change that. It's part of how a material is. And that type of ship gives you certain challenges, potentially, things you need to control, be aware of. You can't let it go out of hand. And there are methods, strategies to handle those ships. It's a very straightforward table. Material, type of ships, challenges, and what to do if the challenge turns out to be a real problem. And the fourth element I was talking about is the operation, because that's something people always overlook. That turning, milling, drilling, deep hole drilling, boring, whatever type of application, it's a different type of machining, and different types of machining leads to different types of ships. So it's not enough to say steel gives me long ships, because if you do turning in steel or drilling in steel or milling in steel, the types of ship, because the operation is different, will be different also. And that itself is a very large subject in the pocket guide, the technical guide I was referring to. I think it's 1/3 of that little book, ship formation in different types of applications. And in that respect, it's important to make that difference. So if you evaluate ships, not only ask what is the material, what are the cutting conditions, what is the tool, but also what was the application. Turning, milling, drilling, whatever. And in that respect, if in general, I would say, if you have to handle ship problems, in turning, feet is the thing you can play with. In drilling, it's more the methodology. Packing during drilling is perhaps something you would love to play with. In boring applications, the cooling that is a key element, and milling is about exit. If you ask me to put one critical element forward. We know how a ship is formed. We know the elements that influence a ship formation. We know how to handle if it gets out of hand. We know what to expect, what not to expect. We know that the workpiece material, the type of application, the tool geometry, and the cutting conditions which are used are 4 big chapters we can play with. If we go to the process now, and if we look to the ships while they are being formed, it starts with that people should actively observing ships. Very often, if it's my experience, if you stand at the machine and watch and talk to the operator, he's very attentive for broken tools, and he's very attentive for vibrations, and he's carefully checking the quality of the workpiece after the operations, and he keeps an eye on the cooling. But the ships, it's part of the game, as I already said a couple of minutes ago. So process monitoring, and based on that, do troubleshooting, starts with actively observing. Actively observing the shape of the ship. Is it spiral? Is it comma shape, needle, ribbon, whatever type of shape? What are the dimensions? Is it big? Is it smaller? The colors. The color of a ship is an indication of the heat which was developed during the process, and to which extent the heat was evacuated away from the cutting zone or was left in the cutting zone. So the color of a ship has a meaning, and most probably, if you carefully observe ship formation, you will see that colors of ships, as the tool goes on cutting, after a while will start changing. So we can learn quite a lot from the color of a ship and the behavior of a ship. Is it flying away? Is it curling around the workpiece? Is it sticking on the cutting tool? Or all that type of things. That is what we have to look for. Because these things give us an indication of cutting temperature. Because I have been defining now a ship as a waste product, often giving trouble. I also have been defining ships as a signaler that tells you how things are going during the process. A third thing we should not forget is that a ship can help us a lot in machining, because Machining means heat generation, and if the heat stays too much concentrated in the cutting zone, that's problematic for the tool and for the workpiece. So we need to take the heat out of the cutting zone, and the most efficient way to take heat out is put the heat in the ships, because the ships normally go away. So the temperature of a ship gives us an indication how much heat is taken with the ship. Tool wear. Ships tells us about tool wear. Ships will tell us if the feed and cutting speed are correctly selected or not. Ships will tell us if the geometry which was selected for the tool is appropriate for the application. And ships will help us to evaluate how evacuation of ships is going. There's quite a lot of things we can learn, and observing ships, and I think here is huge potential into the future for uh, digital help, let me put it like that. Uh, Capture these things in a digital way through sensors, bring it into algorithm environments, but that is future. Today it's the operator who needs to observe. He can see the ships as they are being formed. The operator can, but be careful, feel a ship. What is the shape? How big is it? Is it? Yeah, there's so many things you can feel on a ship, and he hears the process, because different types of metal formation or deformation, which machining is, gives certain sounds, and how a material is deformed to which type of ship it leads, you can hear differences. Troubleshooting, also here it's a kind of a very straightforward approach. What you see listed here are all the types of ships which could be considered problematic. Now, if I take the first line, long stringy ships, now they are not necessarily wise problematic, because these type of ships you will find always when you have to machine aluminium, for instance. But it could be that they become too long, and that it starts to hinder the operation. The operator, he needs to stop the machine. Then the long ships become problematic. So you should not see the ships here as a problem on its own. It's if that property is exaggerated, if long becomes longer, if short is getting shorter. You have to look in it like this. If you have too long ships, the most probably cause is that the feed and geometry combination, geometry of the tool and the feed you use, there is a mismatch. And you have to change both if you want to bring things under control again, or one of the two. So for instance, you could increase the feed, or you could use tools with a better appropriate shipbreaking geometry. I can't give figures here, because too long, there's also not possible, and that's going to be a challenge for the future digital approach to this. When is long becoming too long? And there is no figure for that. So the solution, increase the feeds. I cannot give a figure also. How much should you increase the feeds? Well, till the moment you reach that the ship is not too long anymore. And you see, here comes the expertise part, the experience part around. It's not just knowledge. It's also insight and skill, handling ships. If you do this type of exercise, if you want honestly to start working with ships, not in a way of they are problematic, but in a way of I need them to evacuate heat. If I listen, if I look, if I feel carefully enough, they will give me a signal about the process. If you really start to do that in a systematic way, you should never treat a ship on its own. Never. I have had that in the past. People come to me and they show me a ship. What do you think? I don't know. I see a little piece of metal in a certain shape called the ship. But evaluating if this was okay or not or what, I can only do if I know the environment in which this thing was formed, the application, the material, the cutting conditions. So don't treat ship analysis in isolation. See the total picture. Always, if you do ship observations, check cooling. Because cooling is going to have an impact on how ships are formed, not numerically defined, but is influencing, and especially how ships are evacuated. That's a very strong relation. So keep constantly, because you can rest assured if your cooling is no good, most probably your ships will tell you, and the ships will be no good either. And of course, if you do ship evaluation, know your material, because as I said already, cast iron gives long ships. Short ships. And if you say, "Ooh, they are too short, I want to make them longer," well, I wish you good luck to have long ships in cast iron. It's a big challenge. So know your material, know what to expect, but what you can expect, make sure that you control it. That the random aspect at least is taken out. Observe ships while they are being formed. Is the ship breaking? Is the ship going away? Is the ship changing shape, color, or dimensions while cutting? Once the spindle is stopped, check again, where are the ships? Are they gone from the process, or are they hanging around somewhere? Are there signs of that the ships influence the machine surface? That is things you can only do the moment the spindle stops. And once you have those two, ships during process, the results after the process, then if what you see you don't like, try to figure out what was the main cause. And that's where you have to act. This is a kind of, I call it, it's a built-in feature in that global ship formation analysis. How to do the analysis. Ships are process feedback. Ships are waste. Ships are a needed element in machining. Think on heat that needs to be taken out. But ships also are signalers. Ships do process feedback. And if you look to it, if you look to ships, if you evaluate ships, it should not just be, I want to solve a technical problem. I want to break the ship. It should also be, what can I learn from the process which I just had or which I am having? What can I do there to improve? That is what we aim for. Now, the hidden cost aspect, which I already mentioned, ships really are hidden cost creators, because if a tool breaks, that makes a lot of noise. Everybody in the workshop hears that something is wrong. But ships not. And if there are negative things connected to the type of ships you have, because the machine is stopping, because the operator needs to take out the ship, so your tool life is reduced because the ships are hurting the cutting edge, or the quality of your machine surface is deteriorating because the ships are interfering with the machine surface, it's all going on quietly. And the results are hidden till in the end you do the final analysis. So ask people in the workshop to keep an eye on it. If you notice that a machine is standing still regularly, check with the operator, why is the machine standing still? It's just a question, and perhaps it gives you just an answer, because I have constantly long ships I need to remove. Simple. Log that. Measure the lost time due to ship formation or evacuation things. Part quality, this is something that is underestimated, but next time we are going to talk about boring applications here. And in boring applications, more than in other applications, boring. If you see certain quality issues on a workpiece, they go back directly to ship formation during the process. So if you have quality issues with finished workpieces, it could well be that they point to certain hidden ship formation / evacuation issues during the process. Environmental sustainability thing. Yeah. If ship creates loss of efficiency, of course that is going to influence the durability of an operation. The recycling of the ships is influenced by how ships are formed and evacuated. It's very clear that between ships and how they are formed and the result of that and how they are evacuated away out of the cutting zone influences these things. Most important, I already said, if I in the past had talks about this with people in a workshop, it's so often heard by me that people say, yeah, but it's the game. It's how it works. We cannot do anything. Aluminium gives long ships. And I think that accepting is where it all starts. There are types of ships, but an operator should still have an unhappy feeling about certain types of ships and an ambition, a motivation to try to influence it. And yeah, for me, that's a culture. I can give as much knowledge as you want about ships and how to influence them. But if that motivation, that mindset of I want to improve is not there, then nothing happens. Mindset change, a very critical element if you talk about ship formation, ship evacuation. Mostly people say, it's waste, ships are waste, but ships are a lot more than that. And if you handle ships in a correct way, they can give you some strategic leverages to improve things. And keep an eye on the ships is my message here. If you have ship control in the best possible way, and if you manage to have your ships well evacuated out of the cutting zone, the advantages are multiple. In general, you will notice that you can take profit of longer tool life. If cutting edges are less damaged by certain types of ships, of course it gives you less wear per time unit, per workpiece, which is finished. It leads to longer tool life, and longer tool life leads to a lot of advantages. Not just lower purchasing budgets for the tools, but also lower stops to change tools and stuff like that. It gives you improved part quality, more consistent part quality. If ships are constantly scratching on machine surfaces, if you constantly suffer from build-up edge problems, that is going to endanger the quality of a finished workpiece. If you have your ships under control and if you evacuate them well, you have a more stable process, which is very important. If you want to scale up the process, you want to produce 10,000 workpieces in a very stable, reliable manner, or it gives you the opportunity to handle variation more efficiently. I mean with that, if you have small batches to machine, perhaps even one-off batches, if you have a stable process which you fully understand, the chance is bigger that your first time yield, as it is called, do you manage to finish a workpiece the first time right, is going to improve also. It's going to reduce unplanned stops. Stops because you have to handle problems. And if you have lesser unplanned stops and lesser time to spend to solve problems, that gives you automatically an increased capacity for the machine tool, which is from a sustainability perspective and an economical perspective a very interesting result. lower energy and cooling consumption, because while a machine is standing still, just to give an example, while a machine is standing still to handle a ship evacuation problem, the machine is still kind of on electric power, consuming electricity, doing nothing. It's a very simple example, but it's there. Easier automation. If you are thinking of using unmanned production, put a robot, a manipulator to handle workpieces, tools, and so on. You have to have, because robots do not like long ships. If a ship is around a workpiece, for a robot that's very problematic. And last but not least, operator engagement, operator frustration, morale is going to improve, because those bloody ships always problems, always you know. I have to keep my eyes on the time. This and so much more, again, as I said, because I'm rather sure you are still sitting there with a lot of questions. What about this? What about that? I would advise you this, where you find a lot of answers on questions you most probably have. But let me first check the questions we have during this presentation. One question is ship formation in titanium and Inconel the same, as they both belong to the ISO S material group? And he who asked the question said, because I have my experience is that they are different, and you are very right in that experience, because ship formation in titanium and ship formation in Inconel are different. I know they both belong to the ISO S group, the high strength materials, super alloys, but there are properties that they have properties which make that there are in details differences in how ships are formed. Another question, is it correct to say that shorter ships are always better? No. Shorter ships, better, shorter ships gives you lesser problems with ship evacuation. But shorter ships will give you also more issues on a cutting edge during to fluctuations in cutting forces, in heat generation, engagement times which change all the time. Shorter ships could lead to, if they are too short, leading to too big variations during the process, could lead to short tool life. So and that's a bit the balance you have to find. Shorter is better for evacuation, but too short is not so good for the behavior of a cutting tool. It could lead to short tool life, fast developing wear, crashed tools perhaps. So it's a matter of keeping a balance. Another question is, can ship formation lead to vibration problems? Yes. I would say ship formation, with the exception of long ships, but all the other ship forms, serrated ship, discontinuous ship, build-up edge ships, leads to variation in cutting forces. And if you have, let me try to show it. If you have a long ship, if this is your tool, the ship is going to do this. If you have a short ship, the ship is kind of going to do this. And this thing is something a cutting tool does not like, because this thing creates micro vibrations, and micro vibrations lead to potentially lower cutting tool life due to higher wear and irregularly shaped wear, and is also leading to quality for the workpiece, which is dangerous. we have some time left. Some more questions. Somebody is asking temperature visualization. It's not been taken care in this presentation, but I don't remember the number. We had a previous Getting Technical Live event, and you can find it on the website from SECO, I suppose, where we were talking about temperatures and stuff like that. And there you'll find a lot of information about temperature and temperature gradients and heat generation during machining and so on. But here today I did not take care of it. Another question: how does the introduction of low high feed oscillation dictates which type of tool geometry should be used during the turning process for the given materials? Yeah, of course, the moment you change the strategy, the technological strategy of what you want to do during machining, yeah, of course, that's going to influence the tool selection. Those two are yeah. Also there, we talked in a previous Getting Technical Live event about how do strategy, geometry, cutting conditions combine. And if you modify one of the three, always the other two needs to be changed to be adapted to the new whatever of the three you changed. So the question is yes. Another question. In the workpiece material, which characteristics will determine the type of our ships? Just the hardness, mechanical? No, it's a combination of hardness, of course. If you have harder workpiece materials, that leads to lower ductility. So next to hardness, ductility is an important element, because high ductility means you can deform the ships a lot without breaking them. Higher hardness, meaning lower ductility, means just the opposite. But also things like abrasiveness or adhesive nature, leading perhaps to build-up edges during machining. And if you have a build-up edge, that influences ship formation, play a role. And even thermal elements play a role, because ship formation counts on kind of, especially in the harder materials, a softening element during machining. If you have a very hard material, it's very difficult to deform, and machining is deformation. Deformation until it shears off. Now, if you have a hard material and you try to deform it, the hardness is resistance against deformation. So harder materials, it's more difficult to machine. On the other hand, if you can count on that the heat which is generated during machining stays in the cutting zone, that heat will pile up, create higher temperatures, and you know what happens if you submit the material to higher temperatures. It softens, which makes it easier to machine. It's a crucial element when you start using synthetic cutting materials. I think on PCBN and so on, their heat is important, and how much heat which is generated during machining is depending on the strength of the material. So now I have another property, strength, resistance against deformation, kind of internally in the structure. It's more than just hardness. I should not get lost here because the time is too short. One last question to round it off, and all the other questions afterwards I will take care of in the comments. If you can hear what's happening with the ship, can you then use AI to detect correct or incorrect ship behavior? In theory, yes. In practice, my experience so far, and it's a long experience I have, is that if you want to do in-process monitoring, you need to capture the sound, filter it, transmitted to a data pool, and instantly, have the algorithms that draw conclusions, lead to things that needs to be corrected, and send it back. And that needs to happen extremely fast. And as I said, in theory, my answer is yes. In practice, out of a laboratory, so far I have never seen it working and giving satisfactory results. I want to stop here all the questions, all the remaining questions. Again, I will take care of in the comments afterwards. Thank you for being present here today. I think a very important subject we talked about today, ships. A very underestimated thing. And underestimated, I mainly mean that in the head of people, the mindset. Too much, too often people consider ships as, it's fact of life. And that is, if you have that attitude, you never will get better. Huh? So it starts with I look at my ships in an active way. I try to understand what I see, and based on what I see, that gives me certain conclusions, and those conclusions lead me to action. That's kind of, I hope today I convinced you that ships are more than waste. Ships are indicators, signalers, and if you know how to pick up the signal, you can do a lot based on ships and how they are formed and how they are evacuated. Thank you very much. Next time we are going to talk about boring. Boring is the older people. You remember how it was in the past? A turning tool came in a plastic box. A milling cutter came in a cardboard box. And the boring tool came in a very nice wooden box, very well packed, protected, and that is boring. Boring is an application in machining where it's about precision, where it's about quality, and very often boring is one of the last operations that is done on a workpiece. In that respect, the raw workpiece material before boring is already very expensive, meaning that boring is an application where knowledge and insight to avoid that things go wrong and that I reach the wanted levels of precision and quality is an extremely important application. And we are going to talk next time about boring, how to handle it, how to control it, how to make sure it leads to the wanted results. Thank you very much. Looking forward to see you the next time. And again, if you have questions, put them in the comment. If you want to have a copy of this presentation, let me know. Whatever questions you have, let us know and we'll try to answer them in a good way.